Okay. So hi everyone, and welcome again to the course Introduction to Information Processing and Learning. My name is Ovid, and I will be okay. So as I said, my name is Ovid, and I will be your TA this semester. First of all, I know that it can be a hard course, maybe one of the most challenging courses, especially here at LSEC. And I will try as the best as I can to help you understand everything. But you need to help me to help you, and you can do it by ask questions. Okay? Don't afraid to ask questions during the class. After it, you can. The best way is to post in the discussion forum in the Moodle. I will monitoring it and will answer you there. And if you don't understand something, you can write me an email, and we will find a time to meet and chat. About the assignments. As Sally said, there will be something like 9 or 10 exercises. You need to submit them electronically. We encourage you to submit them to write them in LaTeX. It's a very useful tool, but you don't have to. You can write them by hand and scan them and upload them to the Moodle. Just make sure that Tomer, our checker, can read them, because we don't want to waste his time. Okay? There will be also programming parts in some of the exercises. We don't expect from you to be a super programmer, but you need to know how to take your ideas and your algorithms and to implement them by the code. By the way, is there anyone here that didn't write a code in his life? Okay, great. So today we are going to talk about probabilities and random variables. So let's start with probability. Okay. So, by the way, if you don't understand something, just tell me. So, the notion of probability is related to the uncertainty of the world. If we are doing some experiment, we have some uncertainty in the outcomes of this experiment. Okay? And we called sample space and we denote it by omega, the set of all the possible outcomes of our experiment. Okay? So omega here is a set of all the outcomes. For example, if we throw a die, what is omega? 1 to 6, right? Okay. So now let's suppose that someone threw a die and told us that the result is an even number. Okay? But of course, that even number is not an element in our set. However, the even number is just a subset in omega, or we can call it event A. And A is just a subset of omega. So in our case, if someone told us that it's an even number, what is the subset? 2, 4, or 6 in the case in the previous case, right? Okay. So just a quick reminder about sets. So we say that A bar, or sometimes we also say A with C in the top, is the complement of A, and basically it's the event that A did not happen. Okay, all the elements in omega that they are not in A. Okay. Now we say that if we have two events, A and B, we say that they are disjoint if what? Right. Their intersection, A intersection with B, is the empty set. Okay? So we say that A and B are disjoint. Just notice that both omega and the empty set and the intersection of A and B and their union, all of these are also events. Okay? And one last thing, we called the power set of omega as the set of all the possible events in omega. Okay? And it's 2 to the omega. This is how we denote it. Okay? Any questions? Great. So, yeah. So we have for example, we have if we throw a die, we have all the events. We have omega is 1, 2, 3, 4, 5, and 6. Okay, and the power set of omega is all the possible events that we can get. Okay, is all of our all the outcomes that we can get. No, so okay, so maybe I will try to. Okay, it's also the power set is that we can get that if we throw if we can get I don't know, an even number, for example. Okay, or all the possible events that we can get. It can be also some subsets. It can be all the subsets of omega. Okay. Questions? Okay, now let's talk about probability measures. Okay, so we say that intuitively a probability function assigns for each event in our sample space assign a number that basically it quantifies our belief or our probability or the possibility of observing this number as the outcomes of our experiment. For a function to be, if we define a function P, we say that it's a probability function, a probability measure, if it satisfies 3 conditions. Okay? The first one is non-negativity. That P of A is bigger or equal to 0 for every event in the sample space. The second one is additivity. That means that if we have a set of AI, a countable set of AI events that are mutually disjoint, that means that each pair of these events are disjoint, we can write that P of the union of all these events is equal to the sum of the probability of each one of them. Okay? So here, this is the union, the probability of the union of all these events. And here, it's the sum over the probability of each event. Okay? So this is called the additivity. And the third condition is the normalization, that P of omega is equal to 1. Okay? By the way, I uploaded my notes to the Moodle, so you can look on them after the class. So it just tells us that the probability that something has happened is 1. Okay?
What is the notation into it?
This is a set. It's set of events.
If they're disjoint, what's the...
No, okay, yeah. So this is a set, and now this is we say that yeah, I didn't write that they are disjoint, but they should be they need to be a disjoint. Okay, this is just a notation for set. Question? Okay. So now let's talk about discrete probability spaces. So discrete probability. Okay, so now we are in the case that omega, our sample space, is discrete, and then P, our probability function, is defined over all the possible events. Okay, so we can define P as a function between all the possible events that can be 2, 0, 1. Okay? And in this case, we can fully define P by the values that it gives to all the elementary events in the set. Elementary event in the set is just a single is a set with a single element in it. Okay? So we can say that P of A is equal to sum over all the element events in A, P of this element. Okay, we denote W is elementary event in A, so we go over all the elementary events in A and just sum their probabilities. Okay, now I will show you some properties of a probability measure, but I will not prove it. But it's a good exercise at home if you want to prove it. It's really not difficult. So if we have some function that satisfies the three conditions of probability, we know that, let's right here. Okay, so we know that for every event A, P of A is between 1 and 0. Okay. We also know that the probability of the empty set is 0. And the probability of the complement of A is y minus P of A. Okay? And we also know that if we have two events, two events A and B, that B includes in A, we know that the probability of B is not greater than the probability of A. So if P includes in A, the probability of B is not greater than the probability of A. Okay? Great. Now let's talk about conditional probabilities and independence. So yeah. So conditional probabilities. Probabilities. Okay. So the intuition behind conditional probabilities is that we have an event A, and now we want to ask, someone tells us that B has occurred, and we want to ask what is the probability that A has occurred if we already know that B has occurred. Okay? How much we need to change our belief about A if we already know B. So of course that we need to look on their intersection, but as Tali said in the lecture, we also need to normalize it because now we already know that B has occurred. So B is all our sample space. So, definition. So the definition of A given B. Okay. So this is the probability of A condition condition B. This is equal to the probability of their disjoint event divided by the probability of B. Okay? Great. So, and from here, we can see that the probability of the disjoint event between A and B is equal to the probability of A given B times the probability of B. Okay, so now let's talk about the total probability law. And basically, the total probability law helps us to describe some events with other events that we condition on them. So, total probability law. So now, yes. Oh yeah, sure. So let's suppose now that we have a set AI events when I is between 1 to n. Okay? And this set, these events are disjoint, each pair of them is disjoint. And they are also, the union is omega. Okay, so the union of all these events is omega. And basically we say that they are disjoint, but they describe all of our world, all of our sample space. And now that the total probability law says something very, very simple, that we can describe some event B as the sum over all the AI, the probability of B given AI times P of AI. Okay? We can decompose this event to the conditional probability on the other events. And the intuition behind it is, can you see it? Okay. So, for example, this is our sample space. And now, for example, we have some, this is A1, this is A2, and this is A3. Okay? So, all the events, all the AI describe the sample space. And now we want to ask what is the probability of some other event, B. Okay? B. And we want to ask what is his probability. So the total probability law just tells us that we can sum over this area and this area and this area. Okay? Great. Now let's talk about independent events. So we say that two events are independent that A and B are independent this is a definition of independent if their intersection is, what is their intersection of independent events? Yeah. Right. So if P, the intersection of A and B, is equal to their multiplication. P of A times P of B. And also you can show that P of A given B is equal to P of A. Okay? And the intuition of two independent events is that if we see B, we don't change our belief on A. Okay, so the probability that after someone told us that B has occurred, the probability to get A is the same as the probability to get A at the beginning. Okay, so one event does not affect on the other event. Okay. Now let's talk about Bayes' rule. So independent events are a very specific case of events, right? It's not a general case, but Bayes' rule give us a specific equation for how to find, how to update our belief when we know that, how to update our belief on the probability of A when we know that B has occurred. Okay, and this is the general case, and Bayes' rule just tells us that the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. This term is also called the posterior. And this term is our prior. Okay? So now we know how to update our prior and to calculate our posterior. Okay? Questions? Okay. By the way, you can prove it from the definition of the conditional probability. Very simple. I know it can be a little confusing, the conditional probabilities. Why there is a difference between the probability of A given B and B given A, and why they are different. So let's do a small exercise. Okay, so now suppose that the probability of contracting a disease is 1 over 1,000. Okay? And there is a test that for this disease that is correct given the state of the patient in probability of 0.9, both for positive and negative. And now we want to, let's suppose that the patient took the test and it turned out to positive. And now we want to ask what is the probability of this patient to be sick. So what we need to do? So let's try. The first thing that we need to do if we want to solve these kind of questions is just to write it more formally. Okay. So for example, let's be A is the probability that the patient is sick, and B is the probability that the test came out positive. Positive test. Okay? And now, how can we formulate what is the question that we want to answer on it? Right, exactly. P of A is given B. And now let's write what we already know from the question. So what is P of A? We know that P of A is 1 over 1,000. Okay, now what is the probability of P of B given A and P of the complement of B given the complement of A? What is P of B given A? What is this probability? Yeah, but okay, so yeah, it's the probability that, right, this, just a second, B given. So these two probabilities are probabilities that the test is correct given the state of the patient, right? This is the probability that the test is positive given that the person is sick, and this is the probability that the test is negative given the event that the person is not sick. Okay? So we know that this is equal to 0.9. Now, okay, so now we have this. So what is the probability of the complement of B given A? What? 0.1, yeah, right, because okay, so how we get it? We know that this is equal to 1 minus the probability of B given A, right? And we know that this is equal to 0.9, so this is equal to 0.1. And in the same way, we can get the probability of B given the complement of A. Okay? Now, let's see what is the probability of P of B. How can we find it? What? Sorry, I didn't see it. Yeah, right. From the total probability law, we know that this is equal to P of B given A, P of A plus P of B given the complement of A, P of the complement of A. Okay? And now, when we want to answer the question and to ask what is the probability of P A given B, how can we find it? Based on the fact that we have the probability, all these probabilities. Right. By Bayes' rule, we know that this is equal to P of B given A times P of A divided by P of B. And we know all these probabilities, and if we substitute them, we can see that it's approximately 0.009. Okay, you can do the calculations. I also put them in the notes. Okay? Any questions? Great. So, did you understand everything, Tina? Okay. The next thing that we are going to do is to talk about random variables. So, random variables in many cases, we are interested in some function of the event rather than the event itself. Okay, for example, if you want to ask what is the age of the person who will win the lottery, or what is the square root of throwing 10 coins, stuff like this. So we say that a random variable x is a function between from the sample space from omega to r, to a real number. Okay? By the way, any function on this random variable, any g of x is also a random variable. Okay? So, a discrete random variable, we say that x is a discrete random variable if it only can take values from a discrete set. Okay? And in this case, we say that the probability distribution of x is the set of all the values that are equal to some specific values. So, here, big X here is the random variable. Okay, is a function, all the possible values that X can get. And here, small x is a specific value. Okay, so we ask, what is the probability to get? What is the probability of to get all the values that are equals to all the elements that are equals to some specific values? And in the discrete case, it's the same as to go all the elementary events that get these specific values. So this is also, we say we are writing it as P of X. Okay? When we are writing P of X, what we really mean is this. Okay. So let's do a small short example. Now let's suppose that a fair coin is tossed twice. So what is the probability space? What is our omega in this case? Yeah, to the power of 2, right? And what is the probability of every elementary event in this experiment? What? No, because elementary event is to get something in the first time, to get something in the.
So it's 1 over 4.
Right, 1 over 4. And now let's say that x is the number of times that heads came up. Okay? Is the number of heads in our experiment. And now what is all the possible values that x can get? 0, 1, 2, right. And now we want to ask what is the probability function of this random variable. So what is P of X? What is the probability that X is equal to 0? Right, 1 over 4, because we want that in the first time we will get tail and also in the second time. Okay? So it's 1 over 4. What is the probability that X is equal to 1? Half, right. Why? Exactly. We have two possibilities. The first one is that in the first one we will get tail, and in the second one head, and that in the first one we will get head, and in the second one we will get tail. So we just sum them. And what is the probability that X is equal to 2? Also, right. If you don't understand why, come to talk to me afterwards. And of course, this is all the possible options, so it's 0 else. Okay? Questions? No. Great. Time. Okay. Now let's talk about continuous random variables. So continuous random variables Okay, so here in the continuous case, we need to be a little more careful in our definition. But basically we say that, notice here, the definition is that X is a continuous random variable if there exists some function f that satisfies the following things. So first of all, f is non-negative. For all x, f of x is not negative. Okay? This is the first condition. The second condition is the normalization, that if we take the integral between minus infinity to infinity, f of x dx is equal to 1. Right? And the third condition is that for every interval a and b, p of the probability that x is in this interval and b is equal to the integral between a to b of fx dx. And it means that the probability that x, the random variable x, is between a and b, will get a value between a and b, is equal to when we sum the integral between a to b of the function. And to give you some intuition, if this is our sample space, and this is the event that x is between a and b, and this is f of x, and this is x, this x is f of x, and this is x, and now we have some function f of x, and here it's a and here it's b. So this tells us that the area under the curve between a and b is equal to this area. Okay? Questions? Okay, so we'll take a break and we'll return at 12. Okay, if you have questions, you can come to me. So, now, yeah.
כנראה ממש שולי, אבל כאילו אמרת, אם קיימת פונקציה, ודאי לא תוסיף גם את זה?
מה זאת אומרת? ברמה העקרונית יכולה להיות, כאילו, יכול להיות לך איזשהו משתנה שלא קיים לתוך פונקציה, יכולה להיות, בעצם לצד זה, כנראה שתמיד תהיה, אבל היא כנראה לא יהיה לה תכונות כמו רציפות או כל מיני דברים כאלה, אבל ברמת העיקרון כנראה שאנחנו תמיד נוכל לבנות פונקציה מסובכת כדי לתאר את האיבנט. כנראה שכן, כן, תמיד אפשר, זה נכון, תמיד אפשר לבנות איזושהי פונקציה, אבל כן, אנחנו קוראים לה, זה כאילו, אנחנו קוראים לה
כאילו, קונטיניוס זה יהיה איך הוא מוגדר? כאילו, שאתה
Continuous random variable זה random variable שבעצם הוא מוגדר על ידי הפונקציה הזאת שלו, אוקיי?
על ידי f?
הוא לא, כן, על ידי f. אתה בעצם מגדיר את ה-random variable הזה על ידי f. תחשבי שיש לך, במקרה הדיסקרטי אנחנו דרשנו...
כאילו יש לי random variable ופשוט פונקציה, נכון?
כן. אז ככה, יש לך... יש לך random variable, זה פשוט, זה פונקציה על event. זה מאיזשהו, בדיוק, זה בעצם פונקציה שמתארת לנו שלכל event נותנת איזשהו מספר.
ואז אם זה דיסקרטי, אז זה לא הולך לאן, אני יכולה להגיש שזה הולך. ואם זה קונטיניוס, אז...
אם זה דיסקרטי, את יכולה להגיד שזה הולך מ-2 to the power of omega. את לא יכולה להגיד את זה אם את בזה הדיסקרטי, אם את בקונטיניוס, אם את ברציף. את לא יכולה להגיד את זה, כי אם אומגה הוא רציף, אז את לא יכולה להגדיר את זה ככה. אבל אם אומגה הוא דיסקרטי, אז בעצם את יכולה, תחשבי, כן, יש לך יותר מדי, ברמה אינטואיטיבית יש לך יותר מדי איבנטים. יש לך אינסוף איבנט. לכן את לא יכולה להגדיר את זה. כן, זה לא קאונטבל, בקיצור, זה לא קאונטבל. אז לכן את לא יכולה להגדיר את זה בצורה הזאת, אלא את צריכה להגדיר את זה, את לא יכולה להגדיר את זה ככה, את P, את צריכה להגדיר את F, שברמה אינטואיטיבית זה מאוד דומה, אבל את חייבת לעבור דרך.
זה מה שמלבד אותי שלך, את P ויש לך באופציה X.
אוקיי, בסדר.
F זה השקול של P, נכון?
כן. לא, F זה השקול של P, כן. P, כן, זה probability distribution על random variable. אוקיי? random variable זה בסך הכל, הוא לוקח איזשהו...
זה משהו בתמונה של
כן, בדיוק, בדיוק. זה בסך הכל זה. עכשיו, כאשר אנחנו בדיסקריט random variable, אנחנו יכולים להגדיר את P, כן? אנחנו יכולים להגדיר את P, בצורה הזאת. בסדר? שלוקחת איבנט בפאוור סט של אומגה ומעבירה אותו ל-0.1. עכשיו, כאשר אנחנו מדברים על המקרה הרציף, אנחנו לא יכולים להגדיר את P בצורה הזאת, כן? אבל נזכור ש-P בעצם, במקור זה בעצם, זה פונקציה על איבנטים.
זה כאילו המצב שבו התמונה של הפונקציה X היא רציפה, נכון? זה
התמונה של... לא, כן, לא רק התמונה, זה נובע מזה שאומגה הוא רציף, אוקיי? אז במקרה הזה את חייבת להגדיר את זה באמצעות, אין משמעות בעצם להסתברות שאת תקבלי איזשהו איבנט P of משהו במקרה הרציף זה 0, אוקיי? עבור כל P של איזשהו A שווה ל-0 במקרה הרציף. כן, איזשהו זה. בכלל, כן, זה P של W נגיד. עבור כל W זה שווה ל-0. אבל אנחנו עוקפים את זה על ידי זה שאנחנו בעצם משערכים, אנחנו בעצם אומרים ש-P של W פלוס אפסילון, כן, זה בערך F של W אפסילון. עכשיו זה נכון במקרה שאפסילון שואף לאינסוף, אבל במקרה לאפס, במקרה שאפסילון שואף לאפס זה נכון, זה מדויק. אבל אם זה, אנחנו ממש סביב הנקודה הזאת, אז אנחנו רק משערכים את זה. וזה בעצם מה שאנחנו, תחשבי על זה, אז בעצם אם A ו-B מתקרבים אחד לשני, אנחנו בעצם, ככה אנחנו בדיוק מגדירים elementary events במקרה הרציף. מה לא מסתדר לך?
לא, סתם מתבלבל לי. אז כאילו, האבן זה אינטואיציה?
כן.
פשוט פורמלית.
אוקיי, אז מה פורמלית לא...
לא משנה, נראה לי זה משנה.
כן, בטוח? תעברי על זה, אם זה, אז...
אני חושב שהנפסקה של הפאוור זה...
של מה?
של הפאוור זה...
2 to אומגה? אוקיי. מה זאת אומרת? כי אם אומגה הוא...
אם אומגה יש 6 אלמנטים, אז זה לא...
אז זה הקבוצה... בחזקת אומגה... נכון. לא, מה זאת אומרת? אם אומגה יש... זה בדיוק בחזקת...
לא, אומגה אבל היא לא שווה 6.
היא לא שווה 6. נכון. נכון, אבל... לא... זה פשוט שימוש סטנדרטי כאילו של... אתה אומר כאילו, זה... לא, אבל זה כאילו, זה לא מספר, אומגה. זה לא, אבל זה לא הגודל של אומגה. זה הסט של... לא, זה לא מספר האיברים באומגה, זה הסט של כל האפשרויות.
לא,
מה?
2 בחזקת.
2 בחזקת, כן.
2 בחזקת 6, נגיד במקרה של זמן מאוד
אז סבבה, אבל בסדר, אבל הגודל של, בסדר, אתה יכול להגיד שהגודל של זה, זה כל האפשרויות, זה בסדר, אבל אני לא רוצה להגיד, אני לא רוצה רק להסתכל על הגודל, אני רוצה בעצם, אם יש לי פונקציה, אני רוצה להגיד מה האפשרויות, או מה הסט של כל האפשרויות. מה? אז עבור, מה זאת אומרת? אז
זה יהיה כל האפשרויות. זה כאילו...
זה יהיה, כן, אז נגיד אם אני זורק, אם יש לי, אני זורק מטבע פעמיים, אוקיי? ואני בעצם רוצה, אז בעצם, אז כל element event שלי זה 1, נכון? זה, נגיד עוד פעם, אז x הוא מספר, אוקיי, אז element event שלי זה בעצם tail or head, נכון? tail or head, ב-power of 2. בסדר? זה הסט שלי של כל האפשרויות. זה הסט של אומגה, סליחה. הסט של כל האפשרויות זה לקבל בהתחלה tail ואחרי זה head, או לקבל קודם tail או קודם head ואז tail. אם אני זורק פעמיים, מטבע שאני זורק פעמיים, אז אומגה שווה לסט של head וtail. בסדר? זה אומגה. אוקיי?
כלומר, כן, כל הקומבינציה.
אז הסט של כל האפשרויות, 2 to power of omega, זה בעצם, זה כל האפשרויות, האפשרות לקבל head בהתחלה וtail אחרי זה.
זה לא מספר, זה מנייח את כל הפעולות.
כן, זה לא מספר. זה בדיוק מה שזה, זה לא מספר. זה מה שהתכוונתי. אוקיי? זה סט של כל ה...
זה לא מספר כל
לא, זה לא מספר, לא, בדיוק, זה לא הגודל של הסט הזה, זה ממש הסט עצמו.
אוקיי.
בסדר?
כן, תודה.
אוקיי.
That's the only one with the same.
What about physiology?
No, at least not. Yeah, yesterday is when I tried.
אוקיי.
Already.
סליחה, אני חושב שעד מתישהו בנובמבר את יכולה, אבל אני חושב שאחרי זה את לא יכולה. אבל אם את רוצה, אני יכול לשלוח לך את ה... דבר ראשון, אני חושב שהכי כדאי שצריך לדבר עם נילי, מכירה את נילי? היא המזכירה פה. אוקיי, כן, בגלל זה גם לא קיבלת באמת את המייל. אז תשאלי את נילי האם יש אפשרות כזאת, ואם אין אפשרות כזאת, אני פשוט אשלח לך את הסיכומים, ואם את עושה גם את התרגילים. אז יש אותו במודל, אוקיי, אני... כן, בדיוק. אז זה רביד.זיו שטרודל מייל. כן. בשמחה, ואם זה, אז פשוט תגידי לי ואני אשלח לך אם נלחש עליה.
I just
just want to make sure this notation. So
Yeah.
you mean X is the set, right? No, all the elements. All the
Yeah, X is a random variable.
yeah.
Okay, all the elements that
Yeah.
this random variable can get.
Yeah. And the small x is the
It is specific. Yeah, 1, 2, 3, 100.
Yeah.
Okay.
And what's this?
This is all the elementary events. Okay, W is the elementary event. Is the set, because here it's discrete case, we can fully define P of X by all the elementary events of X.
W is the elementary event.
Yeah, so we say all the elementary events that give this value on X.
All the elementary events.
Yeah, this is elementary event, and X of W is some value that this elementary event gives. This elementary event gives on X. Okay.
This from X. And
Okay.
This is the small x.
This is a small X. So we are going over all the elementary events,
Yeah.
and we say what are the elementary events that give this specific value.
Okay.
Okay, and this is this is the probability.
Okay.
Okay, and
so this is like a function of W, right?
yeah, exactly. X is a
Okay.
function of W because X is a function of the sample space. Okay, X is a function of elements in the sample space.
Thank you.
Okay,
Yeah. Thank you.
great.
所以我们后面还要通过另一个途径去吸收的。OK。Yeah, just make sure that you are in.
But they didn't confirm my just approve your
Okay. So hi again. So before the break, we talked about continuous random variables, and we say that a random variable x is continuous random variable if there is a function f of x that satisfies these three conditions, and if such function exists, in this case, so we call it the probability density function of x. Okay, so we call it the probability density function, or the PDF of x. Now let's talk about the cumulative distribution function, or write it here. The cumulative distribution function, or we also call it the CDF of some random variable x, and now it's defined as, we will first define it for the discrete case and then for the continuous one. So f of x, this is big F, is equal to all the events of x that are not bigger than small x. Okay? And this is also equal to all the elementary events that are smaller than x. Okay, so this is the definition. In the discrete case, f of x is equal to sum over all the values that are smaller, that are not bigger than x, p of k. Okay? And in the continuous case, is just an integral between minus infinity to x, f of z dz. Okay? F of x. So in the discrete case, we have summation, and in the continuous case, we have integral. Some properties about So some properties about the CDF. Properties. So in the limit, when x goes to infinity, what is f of x? 1. Right. To infinity. And in the limit that x goes to minus infinity, what? Yeah. Great. So in the limit that x goes to minus infinity, f of x is equal to 0. And what is the connection between the CDF and the PDF of X? What? Right. So if f of x is differentiable, so then x has a PDF, and the connection between them is the PDF is equal to derivative of the CDF. Okay? Okay, and the final thing, f is a monotonically non-decreasing function. That means for every xj that is smaller than, for every xj that is for every xj xi j is bigger or equal to I, f of xj is bigger or equal to f of xi. Okay? Now let's do some example. So okay, so now let's suppose that x is a continuous random variable, and it has the following density function. So f of x is equal to some constant c if x is between a and b. This is the density function. Sorry, yeah, I know that. And 0 otherwise. Okay? Now, first of all, let's find c. How can we find c? Yeah, exactly. Because we know that the normalization term, we know that the integral between minus infinity to infinity f of x dx is equal to 1, and we know that also. So outside of the interval between a and b, what this integral is, right? So we have only the integral between a to b, c dx, and we know that this is equal to c b minus a. Okay? And we get that c is equal to 1 over b minus a. Question? Okay, great. So now we want to find the CDF of x. So how can we find it? By the definition. So I think it's on the board. Right. So the definition of f of the CDF of x is right. The integral between minus infinity to x f of z dz. Now, if x is smaller than a, what is this integral? What? Yeah, right. If x is between a to b, so if x is between a to b, we know that this is equal to 1 over b minus a. Okay? dz. And now this integral is equal to, what is the integral? This is a constant. So what is the integral? Yeah, x minus a divided by b minus a. Okay. Now, so we know that between a to if x is between a to b, so this is f of x is equal to this. What is this function if x is bigger than b? Exactly. So finally we got that so at the end we get that f of x is equal to x minus a, b minus a if x is between a to b, 0 if x is smaller than a, and 1 if x is bigger than b. Okay? Great. Now let's talk about joint and marginal distribution. So okay, so joint distribution. Now suppose that we have two random variables, x and y, and both of them are discrete, and we want to define their joint distribution. That means what is the probability that this random variable gets some value and this random variable gets some other value. So the definition of joint distribution is P of x and y is equal to P of big X is equal to the specific x, and intersection of y is equal to some y. Okay? So we say that for all the x, y that we have, so the joint solution that this event that this value and the probability of this value and this value is the probability of the disjoint of all the values that y is equal to some specific y and x is equal to some specific x. Okay, and if we want to talk about continuous random variables, we need to be again more careful here, and we say that the joint PDF of two continuous random variables, so x now is in some area dx, and y is in some area dy, is equal to what we need to do in the continuous case. We need to do an integral over all the values that in these areas. So it's an integral of all the values in the area of x and they integral all the values in the area of y, f x y, dx dy. Okay? Questions? Great. Now we say that the marginal distribution of x is equal to how we get the marginal from the joint distribution. What? Yeah, right. So in the discrete case, p of x is equal to sum over all the values of y, p of x, y. This is in the discrete case. And in the continuous case is just integral f of x is equal to the integral between minus infinity to infinity of fxy dy. Okay, so again here we go over all the values, all the possible values of y, and we integrate it. We integrate p of xy. Okay. Now, why this is this? Why this is true? It's small f. It's a probability density function of x. Okay. Okay. Now, just it's important to notice that f of x, f of y, and f of xy are totally different functions. All of them are probability functions, but they are totally different. Okay, they can be. There is a connection between them, but they are not the same function. Okay, so now we would like to extend the definition of conditional probability from events to random variable, and we'll do it in the same way that we did it before. So the conditional probability the conditional probability So the conditional probability of x given some specific value of y, so p of x given y is equal to, what is this? The same way that we did in the event, when we have events. So the conditional probability of x given y is the probability of x and y divided by p of y. Okay? Here we condition, the conditioning is on specific value of y. And so this is in the discrete case, and in the continuous case, again, is the same thing, but with the density function. So in the continuous case, f of x given y is equal to f of xy divided by f of y. Question? Okay, and again, we defined independent events if so independent random variables, as we defined the independent events. So if we have two random variables x and y, p of x, y, if they are independent, p of x, y is equal to p of x times p of y. And the same thing also in the continuous case. It's small f. Yeah, it's not small f. Yeah, sorry about it. It's small f. Now, okay. So now let's talk about. In some cases, we are interested not in the random variables themselves, but in some function on the random variables. Some example of this is the moments of the random variables, and the first one is the mean or the expected value of random variable. So the definition of the mean or the expected value, it's the same thing, of random variable is so if x is a random variable, the expectation of the random variable is just sum over all the possible values of x, px. Okay? I'm sure that you already know it. So some properties of the expected value. If we have any function on this random variable, what is the expected value of this function? So if we have the expected value of some function on x, what is it? It's just sum over. Right, we can go over S, or we can go all the values that g of x can get. It's the same thing, p of x. Okay? If we have, what is the expectation of some constant? The constant, right? And one of the most important properties is the linear, that the expectation is linear. That means that if we have two random variables, x and y, and some constant a, x plus y is equal to right. A, the expectation of x plus the expectation of y. And if x and y are independent, then we know that the expectation of x and y, x times y, is equal to, the expectation of x, the expectation of y. This is true if and only if they are uncorrelated, but we will get to this in a moment. Okay. So this is the expectation of two random variables. Now let's talk about the variance of two random variables, the second moment. Any questions? Great. So I know it's a basic concept in probability that all of you should already know it. But it was just to a quick reminder to that can help you in the course. So yeah. Okay. So the variance. So the variance So the variance of some random variable is defined as for random variable, if you have some random variable x with expected value mu, then the variance of this random variable is the expectation of x minus mu to the square. Okay? So this is the definition. And we can also define the standard deviation, or STD, and this is equal to, and we also denoted by sigma is just the square root of the variance. Okay? So the standard deviation is the square root of the variance, and this is the definition of the variance. Now some properties of the variance. So first of all, the variance is non-negative. That means the variance of x is bigger or equal to 0. And when is it equal to 0? Right. When x is a constant, this is equal to 0. We also can decompose the variance, and it's equal to the expectation of x to the square minus the expectation to the square of x. Okay, we can, if you open here, you will get this. And if we have if we have a random variable x and two constants, a and b, what is the variance of ax plus b? What? Ah, yeah, a square, exactly. A square, the variance of x. Okay? Yeah, it's not linear. Okay. So now, if we have two random variables, x and y, and now we are asking what is the variance of x plus y. So, maybe I will write it. So the variance of x plus y is equal to someone else. So it's equal to the variance of x plus the variance of y plus a term that is the expectation of x minus the expectation of x multiplied by y minus the expectation of y. Okay? And this term also we called it the covariance of X and Y. How much X and Y are related to each other. So we can decompose the variance of two random variables, X and Y, to their individual variance and some term that's called the covariance. And if we have x1 to xn random variables that are independent, then how can we? What is the variance of their sum? Exactly. So only if they are independent, or if they are independent, so the variance of their sum is equal to the sum of their variances. Okay, so let's now look on this term. This is an important term. This is the covariance of X and Y. Okay, so the covariance of X and Y. Let's write it here. So the covariance of X and Y, as I said, is equal to the expectation of X minus the expectation of X times the expectation of Y. Okay, so times Y minus the expectation of Y. And we also, if we open all the terms here, we can prove that this is also equal, that the covariance of X and Y is equal to the expectation of X, Y minus the expectation of X, the expectation of Y. Okay. We also can show that the covariance is symmetric. That means the covariance of X and Y is equal to the covariance of Y and X. Okay, because everything is symmetric here. It doesn't matter. And now, if we have two random variables, X and Y, and two constants, four constants, A, B, C, and D, and we want to decompose the covariance of AX plus B and CY plus D. Okay, so how can we decompose this covariance? So this is equal to A times C, the covariance of X and Y. Okay? Question? And just final, the last property is that the covariance of X and X is equal to, right, the variance of X. Okay, and we say that if we have two random variables, X and Y, we say that they are uncorrelated if their covariance is equal to 0. Okay? So X and Y are uncorrelated if the covariance is 0. And also in such case, the expectation the multiplication of their expectation can decompose to multiplication of each expectation, as we saw in the independent case. Okay, if they are independent, they are also uncorrelated. Okay, and now, okay, I think that's it for today. I will upload the exercise maybe today or tomorrow, and you will have one week to submit it. Yeah, it's basic stuff in probability. It's not difficult. That's it. If you have any questions, come to me, send me email, and that's it. Good luck in the course.